Well, good afternoon, everyone. I hope that you have had a good day for those on the East Coast, and for those on the West Coast, I hope the rest of your day goes very well. So today we're going to talk about, we're going to talk about repair of an oven. This is basically basics of oven repair. Okay, we had 12 people signed up. Looks like we get half of them. I'm sure that we'll have quite a few that will join us and leave again. But thank you for your time today, and I hope that you learn a lot. If you have any questions or comments, excuse me, please put them in the post a comment down at the bottom. If you need to say something, go ahead and type that in, and we'll go ahead and we'll get that question. Try to get that question answered. As you look at the bottom of the screen, you can actually see that my information, Reggie's information, and the Easy Stock information is all scrolling across the bottom of the screen. So without further ado, let's go ahead and get into oven repair. One of the first things that we're going to talk about right here is the agenda, and that is what's contained in a wiring diagram, what to check first, and then common failures with the board and what to look for. All right. So reading a wiring schematic is critical in the appliance repair business. Okay. After this program, you should have most of the basic steps that you need to read and understand a basic wiring diagram. Okay. Number one is power sources. And if you look at an oven, there are actually different power sources in an oven itself. Okay. It comes in at a 240 volt. There is a little small DC power source because you're going to get a lot of the DC components as opposed to the larger components, which are the element things that run on 240 volts. There's also a 120 volt power source that doesn't apply really to an oven. And then we have batteries, and some of the high end units actually do have a battery. One of the units that I got for my parents whenever I worked for Electrolux, it has a battery in it so that the clock actually will stay illuminated. I think it's for 20 minutes, and then it will die out. The battery only lasts about 20 minutes, but it keeps it so that if the power goes off and then comes right back on, it doesn't lose anything. Okay. So every circuit has a power source. It's important to know and understand how the circuit is being powered. Is it AC, DC, or battery? The common symbols are listed on this side on the right. There's the 120, there's a 240, the DC power source, and the battery power source. Okay, so this is the battery. If you look on your wiring schematic that you have, okay, if I'm looking at a battery's power source, if I have longer lines, that's going to be my positive. Okay, this one here I will show you in one of the examples that we have for an oven, that the longer lines are actually are on the positive side. Some of the times there is a positive symbol that points you to the right portion of the right power, and as opposed to the neutral. Then the shorter lines, those are your neutrals. Okay, the battery is a common type of DC power. Is made up of parallel lines, short and long lines. The longer lines are the positive side of the battery, while the shorter lines are the negative. They may also have the positive symbol to help identify the positive side of the battery. Okay. Um, Power sources in more detail. Once again, if you look right here, there's 110, 220. Now I want to call your attention to the 220 because if you look at the very center, there's the denotion of a ground. So this unit right here has 240 volts with the ground. Okay. So does the 110. It has a 240. I mean, has 110 volts. Has a one leg hot, one neutral, and then a ground. So how do I know that my power source has a ground? If I have just a regular, excuse me, if I have just a regular 110 plug, the reason that I have I know that I have a ground is because if you look at the plug itself, the center plug that's in it, that's actually the ground. Then on the 240, it's actually an earth ground. Both of those are earth grounds, and we're going to go into earth grounds a little bit later. Okay, so a DC power source, you may actually find one that actually shows this the way that this is, where there's a positive and a negative instead of the long lines and the short lines. So the DC power source flows in one direction. The symbol for it is the one right here below. So the ground, you see the ground wire there. So let's talk about an earth ground. What exactly is an earth ground? Well, actually, it's exactly what it says it is. I have put 2 earth grounds on my parents' house because their house, like mine, was built in the 70s. So it at that time, whenever we were here at the farm, it did not have an earth ground. My grandfather's used to have this home, and this home did not have the plug that has the little circle in the center. It just had 2 straight lines. Okay, so the earth ground, what happens is there is a outside right next to where the power comes into the home. There will be some type of ground that is actually driven into the ground. It could be copper, it could be aluminum, it could be an aluminum alloy, any of those 3, and then you're going to find a huge connector, and it's about this big around, that's going to be attached to it. Coming out of the box, there's going to be a large copper piece that's 10 gauge. I'm sorry, that's 4 gauge wire. Okay. As I mentioned previously, the ground terminal, earth ground, is physically tied to the chassis, which in turn is connected to the ground wire within the power cord, which finally connects to the earth ground via the 3 or 4 prong outlet. Okay. The 3 prong would be the 110. The 4 prong would be the 220 or the 240. Okay. What does an earth ground actually look like? It's a little difficult to see this right here on the center. You can actually see that larger copper wire that comes down the whole side of this pole, and then down at the very bottom, if you take a very long look at it, you can find that there's the piece that I'm talking about. Okay, so this is the earth ground that I was trying to explain with the 110. So the little round, the off round piece, actually, to me, it looks like a house, a little that you would draw. But this 3rd prong is actually your earth ground, and that is physically connected to the outside. Okay, so let's talk about connections and terminals. Okay, so with our connections and terminals, the terminal, understanding the terminals and the connections. So if you look at this connection on the left side, that's a terminal. Okay, the terminals are a connection point to an external circuit and are noted in the following manner, which is right here, the open circle with the line going through it. Okay, the terminal connections are different and they are noted as solid circles. If you see right here, you see the solid circle that goes around. Okay, so here are the real world examples. Okay, if you look right here, this is your terminal connection. Why is that a terminal connection? Because you have the solid, the filled in circle, and then the other is a non-filled in circle on the bottom. Okay, does anybody have any questions so far? Because next we're going to get into switches, but this is about earth, ground, and right now connectors. Okay, going to wait for just a second to see if anybody has any questions. Okay, so let's start with switches. Okay, there's two kinds of switches. There's an SP ST, a single pole, single throw switch, and then there is a DP ST. Okay, that's a single pole double throw. Okay, so my single pole double throw switch is on the one on the left side here. That's an on-off switch, and on a wiring schematic, that's what it would look like. Okay, the top switch shows that the circuit is in the open position. Then, if you look at the bottom side of that, you can tell that is in the closed position. So I now have current flowing through that. Okay, single pole double throw. What does that do? It directs power to different parts of the circuit. Okay, the route of the power is determined by the position of the switch. Okay, so if you look at the double pole double throw switch, at the top I've got power going through that, and it goes up to the top where it is. Pardon me. Where it is where it is on now. So I have current flowing through that. I do not have current flowing through the bottom leg of that. So that bottom leg of that switch. So at some point, I'm going to have something that will change the flow of electricity, and it could be several things. We're going to go through those next. Okay. So once again, here is a momentary switch. Okay, the momentary switch, if you look at the one on the very bottom, I have no power going through that. But let's say that I've got a dryer, or let's say that this is on an oven, so that we keep it on the oven. We'll say that this is the light switch that goes to the light. So if the oven door is closed, the oven has no power going through it. Once I open that oven door, it turns power to the oven switch, and which in turn sends power to the light bulb, and now I can see in the oven itself. All right, so then once again, there are switches that have two inputs and two outputs. Okay, so since those are single pole, single throw, this allows the switch to control power to two output terminals. Okay, the symbol for this, and then you look right there, that the one on the left hand side of that on the right hand current column, the switch is open, and then for some reason the switch gets closed, and then I have power that goes through both sides. Okay, here is a double pole double throw switch. Okay, so you need to remember these, because in an oven, all of these switches are in this wiring diagram. Okay, so the switches here have two terminals for input, okay, and then four terminals for output. So what happens is, in this position right here, I have power flowing through the first point, and then the third point. So at this point, I've got power going through the first and the third point. So if I hit the double pole double throw and change the direction of the power by opening something, then this would divert down from terminal 1 to terminal 2, and then from terminal 3 to terminal 4. Okay, that would be a double pole double throw. This is what it looks like in your wiring schematic. Okay, so if you look right here on the top left, you're looking at a single pole, single throw switch. Okay, if you look right here, there is a stop and a start built into this. So I know that I have my start and stop. And then if you look right here on the far right side on the bottom, you have another momentary switch that I'm going to use that I have in use. Okay. So let's talk about resistors. Every oven has resistors in it. So the resistor provides a restriction of power to a circuit. For the US, the resistor on the left is what it looks like as we all have more and more units that are showing up from across the oceans. That is going to be the universal symbol, okay, the international symbol. We are moving towards the international symbol. Many of the manufacturers are starting because they now they're importing some of the stuff from overseas, and so some of them are they already use this international symbol, and they have gone away from this US symbol. Okay, that is a resistor. If I have a variable resistor, okay, what is a variable resistor? The resistor can increase or decrease power depending on the external input. A thermistor and a photoresistors are examples of variable resistors, variable on temp and light. So my temp would be my variable resistor. Okay, so that would be there on the same thing, but the one on the right is the one for the international, and the one on the left is for the US. Okay, so that would be a thermistor. So our thermistors would be where? That would be our oven sensors. That's a thermistor. Okay, so reading color codes. One of the things that you really have got to know is what is a color code and what does it mean? What does it mean? Okay, so I need to be able to read my color codes. So resistors usually have like somewhere between a 3 and a 6 band. Most common is about a 4 band. So it indicates resistance, tolerance, and sometimes their temperature coefficient, okay, which is a TCR. Okay. The bands are read from left to right. The reading, the directions is not always clear. So you just need to think that I'm moving from left to right, just the way that we read. Okay. To distinguish the reading direction, the tolerance band width is sometimes printed with a 1.5 to 2 times the width of the other bands. That would tell me which way I need to actually read this. Okay. A larger gap between the tolerance band and the other bands sometimes is noticeable. So it's one of the two ways that it's distinguished which way to read. Okay. If a gold or silver band is present, then they must be at the right end, so they are never used for significant digits. It is also always better to check the manufacturer's documentation or use a multimeter to get the exact resistance value. Okay. In a 3-band resistor, the first 2 bands if I could say that, I'd be in good shape. The first 2 bands represent the first two significant digits, followed by one band for the multiplier. Since no tolerance band is available, the tolerance will always be plus or minus 20%. Okay, that would be my tolerance. Okay, in a 4-band resistor, which is the most common, the first two bands represent the first two significant digits. Okay, the third band represents the multiplier, and the fourth band represents the tolerance. In a 5-band resistor, it just keeps going up. Okay, in a 5-band resistor, the first 3 bands represent the first 3 significant digits. The 4th band represents the multiplier, and the 5th band represents the tolerance. In a 6-band resistor, the first 5 bands they do the same thing that in the 5-band that the first 3 did. So the first 5 bands in the same resistance has the 5-band resistor, followed by an extra band, which represents the temperature coefficient of the resistance. Okay, so color coding is a method used to indicate the resistance tolerance values, which we just went through, and their ratings because of the small size. Color bands used because they can easily be distinguished and cheaply printed on small electronic components. Okay, color coding is also used for capacitors, inductors, and diodes. Okay, when the resistor body surface is large enough, as the large wattage resistors, the resistance value, tolerance, and wattage are usually printed in the body of the resistor. Okay, surface-mounted resistors use a different coding that also uses alphanumeric codes printed on the surface instead of color coding. Okay, the coding is defined in the international standard. So if you go and look up that will tell you exactly what the international code is. Okay, it describes the coding standard for both resistors and capacitors. Okay, so like I said, we're talking about here's our 4-band here. Okay, so if you look at this example, at the very top is a brown band. The next one is a black band. The number after that, the next one after that is another black band. Okay, band. Then the next one is the yellow. Okay, so or the gold. Okay, so the first band represents the number 1. The second band represents a 0. The third band represents 10 to the 0 power, and then the fourth band, which is the gold band, represents plus or minus 5%. Okay, so this calculator will help you identify the tolerance temperature coefficient of a coated resistor by simply selecting the band colors. There used to be, whenever I was first coming up, there was a little saying that you could that told you what the little bands meant. I'm going to have to tell you that I do not remember. That has been filed in my no longer need memory bank, and I can't for my life get it to come back up. Okay, so the calculator supports resistors with 3, 4, 5, and 6 bands. So select the number of bands in the resistor you're trying to identify. For each band, select the color matching table. Okay, the resistance value will be calculated and shown with the maximum and minimum values. Okay, this is a potentiometer. Easy for me to say. It's a 3-prong variable resistor that is used to adjust voltage and current in the circuit. The arrow represents where the input voltage is taken from. The 2 terminals are V plus and ground, and that's the symbols. If you look right there, the one on the US is on the left side. The international symbol is on the right side. Okay. If you look right here, that's my if I go back and go right here, this right here is my variable resistor. This run right here. So I'm going to check between these 2 points with my meter. If I go from right there, I should read 2.5 volts. Okay. This is a 5-volt battery. Okay. And then, of course, I have the ground. Okay. Let me warn you about capacitors. Okay. There are polarized and non-polarized capacitors. It doesn't matter if I have a polarized capacitor or a non-polarized capacitor. I'm going to try to discharge the capacitor. Okay. If I don't try to discharge the capacitor, I could get shocked, especially if I was working on an air conditioner. That has enough capacitance going through it that will actually burn your fingers. Been there, done that. Got the T-shirt. Don't want it again. Same thing with a capacitor on a microwave. That will scare you more than anything else, and you end up cutting yourself because you're pulling away from the capacitor. So always try to discharge your capacitor. Okay, non-polarized, they have no polarity, so it doesn't matter where you place it on the negative or the positive side. They usually have a smaller value. Okay, if I have a polarized capacitor, I will always have a plus sign. Okay, on the leg of the circuit, on the positive side of the circuit. Okay, they usually have a higher capacitance than the non-polarized counterparts, and they show the proper placement. Okay, so I'm going to have the plus sign on the flat side, and then the sign that has the half moon. That's going to be my negative side. All right. The other thing, diodes. We have diodes in every single unit that we have for an oven. Okay, even the cheap diodes have diodes. I mean, the cheap ovens have diodes in them. Okay, all polarized device that allows current to flow in only one direction. We have an anode and a cathode. Okay, the positive is the anode. The negative is the cathode. The flat edge of the triangle is the anode side, and the line is the cathode side. So I have shown you right here where those are. Okay. So if we're going through, if you look at this, this is a 5-volt circuit. I get 5 k ohms on each one of the first two. On this line going that's down, and then I have a 2.5 k ohm resistor. Then I also have my R1, which is 4.7 k ohms. All right, and then I have my sorry about that. I'm sorry. I guess we did go back. This is my diode that's right here in the center. Okay. So inductors is a passive component that create a magnetic field when current flows through them. That's the symbol for a inductor. Now, if I put two of these inductors together with a steel I get a transformer. So the transformer either steps up voltage or it steps down voltage. Okay, they're made up of two wire coils wrapped around an iron core. Okay, the symbol reflects that there are two coils on each side of the iron core. Okay, this is a transformer. Almost every single oven out there today has a transformer in it. Okay, so if I look at this, okay, I have this huge transformer right here on the bottom. Okay, this is actually a microwave. If I do not check try to check the voltage on the high side of this. I can try to check it on the low side. And then, how do I know what, well, missed it. Okay. If I'm checking on my transformer, how do I know which side is the low side and which side is the high side? Okay. The low side of my voltage is going to be the one that has the thicker wire. Okay. My high side has got very thin wire, and that's the step up. And like I said, this one actually is a microwave, because if you think about it, there are a lot of combo microwave ovens. So we have the one that I used to have at my house in Daytona Beach. I had a single oven on the bottom, and then my microwave was put together on the top, and it was all built together. Okay, so I would have to have all of this information for my thing. My relays, okay? Relays are electronically operated switches that are basically electromagnets, that open or closes when current is applied to the coil. Okay, so if I have positive and negative going through here, once it has power set to it, it will actually cause the coil to pull the switch open or closed. Okay. A speaker. All ovens now have speakers. How do you know? Well, because you get a tone. Either you get a tone whenever it starts to cook and you've reached a temperature, or you get a tone whenever it finishes the cycle. So they all have speakers in them now. Okay. So right here is a transformer. You see that one? Then we have the single single throw switch right there. We have right there. You can also see the door switch that we were talking about, where it would send power to the light. Okay, so if my indicator light went on this diagram, which points would I check? Okay, I just told you where it go. I go between 5 and N, which is neutral, or 3 and N. I'm sorry. I looked at it and thought it said 5, but it's 3. All right. If I have a gas oven, how can I tell that I have a gas oven? So if I have a gas oven, I have got to have an igniter, and I'm going to if this was a gas oven, I would have the igniter that would show up in the valve. So if you look right here, you have a broil ignition and a bake ignition. So that would show me that's my igniters. So if I'm looking for the temperature probe, where would I actually check it? I would do it one of two ways. I can either check it right here on the board, which would be pin number 1 and pin number 2. Okay, that would check my oven probe, my temperature probe. Okay, if I were to check my door switch here, once again, I'm going to have to go between. This is our momentary switch. Okay, a momentary door switch. Okay, and there it goes to the lock motor and I'll spit it out in a minute, and to the light. Okay, so that's my door switch. Okay, so with a quick look, is this oven electric or gas? I already told you that it was going to be gas because I have igniters. Okay, this one here is the door switch. Okay. Once I open the door, it pushes down and I have power that comes down and it actually turns the oven light on. If it stays up, I can lock my door, and that will allow me to put the unit into a excuse me. That will allow me to put the unit into a self clean. Okay. So how do I check elements on a range? Okay. So if I come in and I walk in and the customer has called in the office and has told the person there, I just don't get any heat. Nothing comes on. I may put it into a bake cycle, but the bake element never comes on. So the first thing I'm going to check, I'm going to make sure that the breakers hasn't tripped. Okay. So then if my breaker has not tripped, one of the things that I need to do is I need to put it into I need to put it into a bake, and then I'm going to test and see if I have 240 volts going through that. So how do I test my element? Okay. So I can check the bake and broil elements, and I'm going to use my multimeter in the lowest ohm settings or use the resistance sound mode. This would tell me if my bake or broil element is bad. If it's my bake or my broil element is working properly, of course I'm going to get the sound mode is going to give me a beep, and then I know that I have a different problem. So at that point I'm going to have to pull the oven and going to have to look and find out why. Okay. If your bake or broil element reads between 30 and 100 ohms, if I don't read between 30 and 100, I'm going to need to replace the element. This one on this example actually had 46.3, so I fall between that 30 and 100 ohms. So that tells me that I have a good element. Okay, here's my bake or broil element. If it's bad, I'm going to go through right here. This is the easy way to do it. If I've got one, if I've already pulled it out. Most of the time, I do not. I'm going to have to go either through the back of the unit, or I'm going to have to pull. I'm going to have to expose the element and pull it out. Okay. So if you look right here, this is my bake and my broil elements. Okay. If I look on the bottom, I can see my bake. Now, I probably at this point can probably do this from the front and not have to worry about about sliding the unit all the way out. But for us, we're going to talk about this. All I have to do is unscrew it, slide this element out a little bit, and I can check to see if my element is any good. That way I don't have to pull the unit. Okay. First, I'm going to remove the door. This is on a unit that has a hidden bake element. Okay. A lot of the elements today all have a hidden bake element. Okay. First, I'm going to remove the door of the oven. You don't have to, but for me, I'm a fat guy, and it makes it a whole lot easier for me to just remove the door. And then once I remove the door, I can set that on a blanket, and I can I can get right to it, and I don't have to worry about getting everything hung up with me trying to getting into the bake element. Okay, so once I'm going to do is I'm going to remove that door. Once I remove that door, I'm going to go down and I'm going to remove every one of the racks. Okay. Then after I do that, I'm going to need to remove these hidden bake element screws. Once I do that, I always had a scratch all or a thing to put putty on I have a putty knife so that I can lift this up from the back, because I've got to actually lift up on it, pull it back, and then I can take it out of the unit. If I do that, okay, once I do that, it exposed this right here. Okay, if I find that I need to replace this, like I said, I can do this from the front, but there are 4 screws that I have to take out. They could be Phillips head, they could be Torx head. There's all. I have seen a flat head, which you don't like, but it could be a number 2 or a 1/4 inch nut driver, or it could be a Torx bit, or it could be a 5/16. It just kind of all depends on the manufacturer. So I'm going to take and I'm going to remove those 4 screws after I have shut the oven off. Okay. Then I'm going to lift the element so that you can get to the wires and get it through the oven cavity. You can disconnect the wires to ensure they don't slip through the back. I used to keep a pair of give me a second. I got to think of what they're actually called. That a surgeon uses it to run a needle through your body a lot of the times, if I'm getting stitches. But I can clamp on that and it won't release, and then I don't have to worry about having to pull the oven. There's nothing worse than ending up having to pull the oven because that element wire slipped to the back. Because now I got to replace everything. I got to take all the screws out of the back, and then I got to get to it. Okay, so I'm going to disconnect the wires. Then I'm going to replace in the opposite directions as I did for the removal of the terminals. I'm going to double check those, make sure that they fit tight. I'm going to look at the wire whenever I pull it. Whenever I pull the element out, I have to double check the wire to make sure that it hasn't had buildup on it. It could have that, the wire itself could have melted a little bit. At that point, I'm going to have to replace the terminal. If I replace the terminal, I have to use a good, I have to use a good, I have to use a good terminal end, and I also need to have a ceramic wire nut, because if I use a regular wire nut, it's going to melt, and then I'm going to be back. Okay, so I'm going to replace it. Once I get all of that ready, I'm going to replace it and put everything back together, and then after I check the brake, after I make sure that it's back and I don't have anything touching, I can put all the screws back in. Once I do that, I can go back out and flip the breaker on it, and then I can check to make sure that it's going to heat. Okay, let's talk about the broil element. So to remove the broil element, there are 4 screws on it also. 4 screws that have to be removed. Right here, you can see where the 2 of those 4 are, and then there's the other 2 that you're going to need. Okay, that's 2 for the front, 2 for the back. Okay, so as I do that, I'm going to pull it out slowly. Okay, if you do it too quickly, you may have to pull the oven because the wires have fallen through. In the bake element, it's whenever I usually had problems the most. Okay. So if you need to remove the support on the bracket, here's what you have to be careful of. Okay. And I have done this. I have gone and gotten my broil element. I went ahead and I put it all back together, and I had 2 screws left, and I was like, where did those 2 screws go? And then because I know they go on the broil element, but I look and there's no other piece that's missing. some of the, depending on which model it is or which manufacturer it is, I could have the broil element. I have to remove the the front of the element. It has a support that holds it up, so I need to remove that. It's not all cases, but sometimes you need to be aware, because there's nothing that makes you madder than you have to go and undo everything that you already spent time doing. Okay, so does anybody have any questions about bacon broil elements? You guys are a very quiet group today. Okay, so let's go from an electric oven to a gas oven. Okay, so in a gas oven, I'm going to have to check the igniters. That's usually the thing that goes bad first, are the igniters. And why do those go bad first? Because they actually, unless you have a hidden bake element, the stuff will drop down onto that igniter, and it will cause it to calcify. And once it calcifies, the next time you use it, it actually will burn the igniter up. Okay, if you look right here, this is a good igniter. Okay, so how do I check my igniter? Okay, I have 120 volts. Goes to the oven control. Then I get an igniter. It goes through the igniter and then goes to the safety valve. The safety valve tells the gas valve it's okay to open. Go ahead and let's get some gas. So we get it then and out. It then opens the valve, and the igniter is hot enough. So now it comes and it ignites the gas. Okay, so whenever I'm doing this, like I said, my igniter is usually the first thing that goes bad. Okay, the how do I know if my igniter is bad? How do I know if my igniter is bad? I have had them that the igniter glowed. I mean, usually you can look at it and you can look at the igniter itself and you can see where it's calcified and it's burnt. It's a no-brainer. But I have had them where it was a weak igniter, and whenever I changed, after I realized that it wasn't pulling my 3 to 3.5 amps, and replaced it, it worked fine. So an igniter, I'm going to have to go and have my my amp probe. Usually, if I'm working on an oven, I take my amp probe in with me, because my amp probe will check everything that I need, including a capacitor. It has capacitance on my unit. You don't have to have 4 different meters. I actually have 3 meters. Okay, I have one that's my amp probe that I can check everything with that I need to. I've got one that's my old just multimeter that I have had for ever and ever. And then I have an old throwaway meter, is what I call it, because if I have a good meter, there's nothing worse than blowing the fuse in it, and then you go in and you replace the fuse, and lo and behold, I blew the meter up. I have a brand new meter that was one of these that somebody had sent me to said, hey, try this. Well, if you plug it in the right way, it checks everything that you need to check. But I was actually thought that I was checking DC voltages, but I wasn't. It actually thought it needed AC voltage, and so it blew my meter. I'm sorry, it was the other way around. I thought I was checking DC voltages, but it's actually the AC voltages that I was checking, and it blew my meter. Okay. Does anybody have any questions right now? I'm going to give everybody just a minute. We're up to 10 people now. That's great. Okay, so we've got 6 from 101 Basics. Washer dryer repair, we got 3. Okay, so that's 9 out of our 12. So we're almost there. All right. So my high limit switch. Okay, I'm going to tell you about a guy that I know that if he had a high limit switch that went bad in the back of his oven, to keep the customer to keep the customer happy, he would actually take it out to the garage and drop that high limit switch on the ground, and it would cause the spring that's in the back to reflex, and that would restore power, and it would work. I prefer not to ever have to do that, but the first thing I'm going to do is I'm going to remove the oven from the cavity. Then I'm going to replace the oven on a protection on the floor. Okay, I'm going to remove all the screws to the back of the oven. I'm going to set the meter to the ohms. I'm going to check for continuity. If I have no continuity, then I have to replace that fuse. Every oven has a high limit. What does a high limit do? If I have this oven in, excuse me, if I have this oven in self-clean, it will not allow it to go over 1,400 degrees. Some of them are set for lower than 1,400. Okay, but it won't allow the oven to reach a point that will actually make ignition possible. Okay. Now I will tell you this: if I actually and I had this problem whenever I worked for Electrolux, the builder used a cheap wasn't real plywood. He used that cheap ABS. It actually put burn marks in it, and that was because the builder didn't follow the instructions. If you read the instructions, it tells you that you cannot use that. But the builder thought he was going to pull one over on everybody, and then 6 months later, they're like, "Well, you guys have got to come out here and fix this." So I actually went out there and took one of the teams. We pulled the oven. Had it, sure enough, there was a big burn mark on the bottom. The customer kept saying, "I smell something burning." Well, that's the reason you had it. That's what caused it from almost burning, but starting a fire. Okay, the high limit ended up never flipped because it was on the where the bake element was. So I mean, you've got to follow the instructions, and you have to follow them to the letter. If you don't, there's a reason that those are asked, that you're asked to what to put in the cabinet so that they don't cause problems. Okay, so this right here is my high limit thermostat. There are several different varieties of high limit thermostats. Okay, there's this. If you look at the very center, okay, there's the old. It's almost like a high limit thermostat for a dryer. There's also one that looks on the bottom, looks very similar to that, and it also looks almost like a dryer. High limit thermostat. How do I check these high limit thermostats? All I'm doing is reading continuity. So if you look at this one on the in the center here, this is the one where I was talking about that he would actually drop that on the ground flat and it would help it would reset. The rest of these you can't reset them. Okay. If the meter is reading 0, what does that mean? Is the fuse good or bad? That's my meter right there on the far left. And then I have this fluke that I have that's on the right. Okay. The meter doesn't change or doesn't go to 0. What does that tell you? Which of those would I need to replace? Both of them? One of them? I realize that we're not in a class and I can't get you to give me if you can answer right there in the bottom, put your knowledge to work and type it in and let me know which one. Okay. If the meter changes, doesn't change and doesn't go to 0, is that good or bad? Okay. If the meter just reads 0, what does that tell you? Once again, is that fuse good or bad? Yep. Okay. So one of the things that I have been whenever I was a technician, I actually had a customer that somebody had. You're right. That's correct. So that tells me that the fuse is bad. So the technician replaced everything in it, including the igniter, and it still would never fire. Well, what he forgot was the safety valve runs through the circuit, and if the circuit is if the safety valve is bad, it will never allow gas to come through. Okay, I actually had this happen to me just as I was leaving just like whenever I was leaving my being a technician and became a trainer. I had this problem. Went out with the technician and I'm like, okay, here's your problem. The safety valve is bad. And he goes, no, it can't be the safety valve. There's no way. And so I said, okay. I said, here's my $20. Lay yours up there because whoever is wrong forfeits their $20. So I went and replaced it, and I took my $20 home with me. It got me a tank of gas and lunch. So it will cause the igniter in a gas oven not to light. Okay, so I'm going to set my meters to the ohm scale, the lowest ohm scale, which is 200, or I can set it to the tone. I prefer the tone because that way I don't have to look at it. I'm going to place the lead, okay, one on the terminal and the other on the other terminal. If you can see right here, that's what I've done. Once I do that, if the value shows resistance of 0 up to 0.5 ohms of resistance, then it's good. If it's not, then it's bad. Okay? So that actually concludes our class for today.